Good evening, students. Good evening to everyone. Today, I am discussing about the analog pulse modulation techniques. Okay, my screen is visible to you. Okay, today I am going to discuss about the modulation techniques. First of all, we need to know what do you mean by modulation. Okay, what do you mean by modulation? So, modulation is nothing but it is the process of we are taking information onto a high frequency carrier and we are transmitting. We can call that as modulation. See, I am talking to you, you are listening. So within the room space, you can easily hear my voice. So if you go somewhere, if you go to the long distance, what happens? My voice is not audible to you, right? At that time, what I will do, I will take any mic and I will talk to you. Then the sound will be, the echo will be reached to you. So here, the mic we can call that as a carrier signal. Okay, suppose a man traveling on a bike. The man is nothing but a message signal, and bike is nothing but a carrier signal. So we can call what is meant by modulation? It is the process of putting information onto a high frequency carrier and we perform transmission. We can call that as modulation. Simply, it is nothing but the process by which some characteristic of a signal, high frequency signal, which are varied in accordance with the instantaneous value of another signal, we can call that as modulation. Okay, basically we will be having two types of modulation techniques. What are those modulation techniques? Continuous wave modulation as well as pulse modulation. So what is by continuous wave modulation? Whenever the carrier signal is continuous in nature, that is, it is varying continuously, we can call that technique as continuous wave modulation. See here, when the carrier wave is continuous in nature, we can call the modulation process continuous wave modulation, or we can say analog modulation. What are the examples of continuous wave modulation? Examples of continuous wave modulation are nothing but amplitude modulation as well as analog modulation. So what do you mean by amplitude modulation? The amplitude of the carrier signal which is varied in accordance with the message signal, we can call that as amplitude modulation. Okay, and similarly, what is meant by angle modulation? Whenever the angle of the carrier signal is varied in accordance with the instantaneous value of modulating signal, we can call that as angle modulation. Okay, the angle modulation is mainly classified into two types. What are those? Frequency modulation and phase modulation. So what is meant by frequency modulation? The frequency of carrier signal which is varied in accordance with the message signal, we can call that as frequency modulation. And what is my phase modulation? Similarly, we said right earlier, amplitude as well as frequency. The phase of the carrier signal which is varied in accordance with the message signal, we can call that as phase modulation. Okay, and the other technique which is pulse modulation. What do you mean by pulse modulation? Whenever the carrier signal is here pulse type. Previously in analog modulation, both message signal as well as carrier signal, both are continuous in nature. Whereas in pulse modulation, we are using message signal as a normal low frequency sinusoidal signal, but the carrier is a pulse type waveform. Okay, then we can call that modulation process pulse modulation. Okay, and what are the types of analog pulse modulation techniques? There should be mainly three types. What are those techniques? Pulse amplitude modulation, pulse duration modulation, or pulse position modulation. Okay, and what are the modulation advantages? Mainly, we can able to reduce the height of the antenna as well as we can perform the multiplexing of the signal, and we can also avoid the mixing of the signals. Mainly is used for we can able to increase the range of the communication, and we can allow the adjustments in the bandwidth. We can able to reduce the noise and interference while performing transmission from transmitter to receiver. That's why we are going for the modulation. The first and foremost technique is amplitude modulation. So see here, what is meant by amplitude modulation? We said, right, it is defined as a system in which the amplitude of the carrier is proportional to the instantaneous value of message signal. We can call that as amplitude modulation. So how can you draw that? See, the message signal is nothing but a low frequency carrier signal, and carrier signal is a high frequency signal. And how can you draw that message signal, sorry, amplitude modulated signal? Simply the product of message signal into carrier signal, we can get the amplitude modulated signal like this. Okay, now take the mathematical representation of the signals. So how do you represent the message signal mathematically? Simply m of t equal to am into cos 2 pi fm into t, where am is nothing but amplitude of the maximum amplitude of the message signal. Similarly, how do you write the carrier signal? Carrier signal is given by c of t equal to AC into cos 2 pi fct. What is AC? Maximum amplitude of the carrier signal. So I said, right, how do you obtain amplitude modulated signal? By taking the combined message and carrier signal by product of m of t and c of t, we can get the amplitude modulated signal. So what is that? See, the standard equation for AM wave is S of t equals AC into 1 plus Ka into m of t cos of 2 pi fct. Okay, what is Ka? Ka is nothing but amplitude sensitivity. Okay, then what we are doing? We are obtaining the final expression for amplitude modulated signal. That's why we are substituting equation 1 in equation 3. So what is that equation 1? We know, right? The message signal m of t equals am into cos 2 pi fm into t. That thing here we are replacing. See here, s of t equals AC into 1 plus Ka into AM into cos 2 pi Fm into T cos 2 pi Fct. And we are replacing this thing with a factor mu. What is mu? Which is nothing but modulation index. What is mu? Which is modulation index. Okay. So final expression is S of t equals AC into 1 plus mu cos of 2 pi Fm into T cos 2 pi Fct. Okay, and we are splitting this term. What is that? S of t equals AC into cos 2 pi fct plus mu AC into cos 2 pi fm into t into cos 2 pi fct. And we know, right, the formula, the product of cosine terms. What is that? Cos A cos B equals 1 by 2 cos of A minus B plus cos of A plus B. So simply we are replacing in the expression fourth equation. What is that? AC into cos 2 pi fct plus mu AC by 2 cos of 2 pi fc minus fm into t plus cos of 2 pi fc plus fm into t, where equation 5 represents the finalized AM signal, where here the first term represents the carrier signal and the second term and third term represents the upper sideband and lower sideband. The upper sideband and lower sideband. And this is nothing but the time domain representation of amplitude modulated signal. Similarly, how do we express the frequency domain representation? Nothing but by taking the Fourier transform of the equation. What is that? We know, right? S of t equals AC into cos 2 pi fct plus AC into K into m of t cos 2 pi fct. Do you know, right? If we apply Fourier transform of the signal x of t, we can get x of f. From the frequency shifting property, exponential multiplied by the signal x of t leads to the shift in the frequency domain by a frequency fc. So by taking that into consideration, I am writing this equation. See here, we are having S of t equal to AC into cos 2 pi fct plus AC into K m of t into cos 2 pi fct. And we know, right, Fourier transform of cos of omega ct. Here in place of omega c, nothing but we are replacing 2 pi fc. What is that formula? 1 by 2 into delta of f plus fc plus delta of f minus fc. So by taking Fourier transform to the equation 1, I am writing with this formula AC by 2 delta of f minus fc plus delta of f plus fc. Similarly, because here m of t is message signal, m of f minus fc plus m of f plus fc. Okay, then we are representing its spectrum. I said right, it is having frequency minus omega to omega. This represents the spectrum of the message signal, and we said right, carrier frequency of the signal, which is minus fc2 plus fc, and this is the spectrum of AM wave. We said right, upper sideband it is having lower sideband. Okay, this is about, and what is the bandwidth required? This is very important. They asked how much amount of bandwidth required for transmitting the AM wave, which is nothing but twice the modulating signal frequency. The bandwidth required for transmission of AM wave is twice the modulating frequency. Okay. In the previous years, they have asked this bit also. What is the bandwidth required for AM transmission, FM, 2FM, like that they are asking. And it is also very important. How do you define modulation index? Which is nothing but the ratio of change in amplitude of modulating signal to the amplitude of carrier signal. We can call it as modulation index. It is denoted by factor mu, which is ratio of AM to AC. Okay, and these are very important, power content in the AM waves. So we know, right, just now we have written the final expression for AM wave. What is that? It consists of carrier component and two sideband components. S of t equal to AC into cos 2 pi fct plus mu AC by 2 into cos of 2 pi fc minus fm into t, right? So it is having three components. One is carrier, upper sideband and lower sideband. Then what is the total power contains in here? The total power in AM signal is nothing but it is the summation of carrier power and the sideband powers. So first we write the expression for carrier power. So we know, right, what is the carrier signal? PC equal to AC into cos 2 pi fct whole square. Okay, and what is here AC? Maximum amplitude of the carrier signal. And so how do you represent the maximum amplitude of the signal, which is nothing but root mean square value. Vrms equal to Vm by root 2. We know, right, the root mean square voltage value Vrms equal to Vm by root 2. Similarly, AC, that is maximum amplitude of the carrier signal, AC RMS is nothing but AC by root 2. And we know, right, formula for P equal to V square by R, where V is nothing but voltage, here voltage is nothing but Vrms. So maximum voltage is nothing but here AC by root 2, right? So that is AC by root 2 whole square by R. So what is the formula? Power P equal to AC square by 2R. That is nothing but carrier power. And similarly, how do you get the expression for sideband powers? P LSB equals mu AC by 2. Why? Because here what is the formula for, if it is AC means AC by root 2. Here it is mu AC by 2. That is mu AC by 2 root 2. So it is 2 root 2 whole square, nothing but 8, right? That's why here mu square AC square by 8R. So what is the total power? Relation between the transmitted power as well as carrier power. What is that formula? The relationship between the transmitted power and the carrier power. Pt equal to Pc into 1 plus mu square by 2. What is mu? Which is called as modulation index. How can you define modulation index? The ratio of message signal to the amplitude of message signal to the amplitude of carrier signal. So it's simply Pt equals Pc into 1 plus mu square by 2. Okay, if you substitute mu value as 1, what happen? We'll get the Pt equals 1.5 into Pc. Okay, this is about the amplitude modulation. Now we see what are the modulating methods for generating the amplitude modulated signal. So what are those modulated methods? See, the devices which are used for generating an amplitude wave, we can call that as amplitude modulator. Okay, mainly we'll be having a switching modulator which is responsible for generating the amplitude modulated wave. See, we'll discuss that. So what is that switching modulator does? It is a device which is responsible for generating the AM wave. See the block diagram of switching modulator. What happened? We are applying the message signal along with the carrier signal here to the diode. So whenever we are applying positive cycle, the diode becomes on, it allows the signal. Whenever we are applying negative signal, the diode becomes off, so it will not allow the signal. Okay, here we are using a diode as a switch. We are applying a carrier signal and message signal simultaneously. I said right. Let's see what is the signal we are applying. A combination of message signal and carrier signal from this here. M of t plus C of t. Message signal is low frequency signal. Carrier signal is a high frequency signal. Okay, V1 of t equal to M of t plus C of t. Then what is the output of diode? We said right, V2 of t equal to V of t whenever the carrier signal is greater than 0. So we are sending positive cycle means the diode becomes forward bias, then carrier signal voltage is high, so we can receive the voltage as V1 of t. Whenever we are applying negative cycle, the carrier signal is 0, simply we are getting no voltage. So the diode voltage will be varying between 0 to V1. Then how do you write the output of the diode, which is simply V1 times the rectangular pulses. See, how do you write V2 of t equal to V1 of t into Gp of t. So what is V1 of t? We said right, a combination of message signal and carrier signal. So message signal is M of t plus AC into cos 2 pi fct into Gp of t. What is Gp of t? Nothing but a rectangular pulse train. We are representing Gp of t with a Fourier series expansion. What is that? Gp of t equal to 1 by 2 plus 2 by pi cos 2 pi fct. So we are substituting this equation 4 in equation 3. So what is equation 1? This one. V1 of t equal to M of t plus C of t. What is equation 2? V2 of t equal to V1 of t into Gp of t. So what is V1 of t? We are sending that signal. See, I am substituting equation 4 in equation 3. See here, in place of Gp of t, I am substituting this here. See here. So what happened on substituting? 1 by 2 m of t plus 2 m of t. This represents the message signal, this represents the AM wave, and this represents the higher order harmonics. So this thing should be eliminated. So what happened? V2 of t equal to m of t by 2 plus 2m of t by pi into cos 2 pi fct plus AC by 2 into cos 2 pi fct. Here we are expanding this term. So which is higher frequency component that should be eliminated by passing through the some filters, some low pass filters. So what is that? The required AM centered at Ft is obtained by passing V2 of t through the some filter, okay, which is having frequency F. So what is that? The total output simply 2 by pi m of t into cos 2 pi fct plus AC by 2 into cos 2 pi fct. Okay, so I am writing this as, see here, 2 by pi into, so we are here, I am taking common as AC by 2 into cos 2 pi fct. So we are doing simplify analysis, so that what we are getting, AC by 2 cos 2 pi fct plus into 1 plus 4 by pi AC m of t. Okay, if we are assuming this term as Ka, how this equation appear? Same, right? S of t equal to AC into 1 plus Ka m of t cos 2 pi fct, which is nothing but our amplitude modulation. So using switching modulator, we can able to get the amplitude modulation. Similarly, we go for the demodulation. So what is meant by demodulation? which is the process of recovering the message signal from the modulated signal. We can call that as demodulation. What is that? Demodulation, the process of extracting a modulating signal or baseband signal from the modulated signal. It's called demodulation. Demodulation is the process in which the message is recovered from the modulated signal at the receiver, which is called as demodulation. So mainly you will see the demodulation as a envelope detector. This is the best example. So what is it by envelope detector? Nothing but it is used for extracting the message signal from the modulated wave. Simply, what is that envelope detector? It uses the circuit which extracts the envelope of AM wave. Envelope of AM wave is nothing but the message signal, which is nothing but the message signal. Okay, see here we are applying amplitude modulated signal, so which is applied to the some transformer. It allows only the low frequency signal and eliminate the high frequency signal. Okay, so when it is allowing positive cycle, then the diode will be in on. Whatever the input we are applying, it should be reaches. When we are applying negative half cycle, then the diode will be off, so it will not allow. Okay, see here, whenever for positive cycle the diode will be conducting, the capacitor will be charged to the peak value. For negative cycle the diode will be reverse biased and it does not conduct, the capacitor will be starts discharging. See here, see, during positive half cycle it reaches, the diode will be on, capacitor will be charged to the peak voltage. Okay, it reaches. And during negative half cycle the diode will be reverse bias, it should be in off state, so whatever the voltage it should not reaches, so capacitor simply it is going to start to discharges. Okay, so graphically we'll draw like this. Okay, so during positive cycle the capacitor will be in on state, the diode will be in on state, it should be charging. During negative cycle it starts to discharges. Okay, this is about your amplitude modulation. Okay, we'll see some small problems regarding the amplitude modulation now. See, so what is that? The carrier amplitude after AM wave varies between 4 volts and 5 volts. Calculate the depth of modulation. So we know, right, the formula. What is modulation index? Which is nothing but the ratio of maximum voltage to the minimum voltage. That is carrier amplitude to the message amplitude. The ratio of message signal to the carrier signal amplitude. Simply mu equal to A max minus A min by A max plus A min. They have given voltage between 4 volts and 1 volt. Simply mu equal to 4 minus 1 by 4 plus 1. So it should be 60%. Similarly, they have given the carrier wave is represented by the equation EC of t equal to 10 sine omega of t. Draw the waveform of an AM wave for mu equal to 0.5. So we have to draw the waveform. So what is the given data? EC equal to nothing but the carrier signal. What is 10 reference? The carrier signal amplitude. So AC equal to 10. And do you know, right? How do you define the modulation index? We know, right? Which is the ratio of amplitude of message signal to the amplitude of carrier signal. So from this, AM equal to mu into AC. Why? Because we know the value of AC. We need to know the value of mu. So that AM equals mu into AC. So mu they have given, right, which is 0.5, and AC they have given. So we need to find the value of AM. So which is 5 volts. And what is the maximum voltage? A max equal to AM plus AC, which is 15 volts. A min equal to AC minus AM, which is 5 volts. So in this way, we need to draw the diagram. Okay, this is one type of problem. Okay, next we'll see the another problem. Sorry. Like this, they will be asking the main problems. Now we are going to discuss another technique, another pulse modulation technique, which is frequency modulation. What is that? Frequency modulation. So here, just now we said, right, under angle modulation. What is meant by angle modulation? Just now I said where the frequency or phase of the carrier signal is varied in accordance with the message signal. But here the thing is only either frequency or phase of the carrier is varied with respect to the message signal. But the amplitude signal, its amplitude remains constant. Okay. So what is it by angle modulation? Whether frequency or phase of the signal is varied, we can say that which is angle modulation. They are classified into two types. What are those? Frequency modulation, phase modulation. Mainly, exclusively, angle modulation is used for the applications like radio broadcasting and television sound transmission and radio communication, cellular radio communication, and microwave and satellite communication. For that purpose, we are using that angle modulation. So how do you define angle modulation? Where the phase angle of a sinusoidal carrier wave is varied with respect to the time. How can you represent mathematically? S of t equal to EC into cos of omega ct plus theta of t, where EC represents peak carrier amplitude, omega c represents carrier frequency, theta of t represents instant phase deviation. And we write the theta as function of em of t, where em of t is nothing but em into sine omega t. And the modulated wave, the total angle modulated wave is nothing but S of t equal to EC cos theta of t, where EC represents the maximum amplitude of the carrier signal. So which is maintained constant, where theta is nothing but it should be frequency modulation or phase modulation. See, theta is angular argument which varies in proportion with the message signal. Okay. Now we'll see the frequency modulation technique. So first phase modulation. First we see phase, after that frequency. So what is phase modulation? We said, right, phase modulation is a type of angle modulation in which the phase angle is varied in proportion with the amplitude of message signal. So what is that phase modulation? Where theta of t equal to 2 pi fct plus kp into x of t, where 2 pi fct is nothing but angular argument. Okay, x of t is nothing but message signal. Then how do you represent mathematically? We said, right, S of t equal to EC into cos theta of t. In place of theta of t, what is that? 2 pi fct plus kp into x of t. Okay. Then now we see similarly frequency modulation. So what is that frequency modulation? Where the frequency of the carrier signal is varied in proportion with the instantaneous value of message signal. So what is that? Fi of t equal to fc plus kf into x of t. So how do you define? Theta of t equal to 2 pi fct plus 2 pi kf integral 0 to t x of t. So the general mathematical expression for frequency modulated wave is S of t equal to EC into cos, in place of theta of t, what is that? 2 pi fct plus 2 pi kf integral 0 to t x of t dt, which is the frequency modulated wave, general mathematical expression. Okay, now we see the graphical representation. How do you represent? This is the message signal and this is the high frequency carrier signal, and we know, right, in amplitude modulation the amplitude will be varying. That's why here maximum amplitude, minimum amplitude. In frequency modulation we said, right, so whenever there is high frequency, high amplitude, there should be high frequencies. Whenever there is low amplitude, there should be low frequencies. where the frequency of the carrier signal is varied in accordance with the amplitude of the message signal. See here, as the amplitude keep on increasing, there should be frequency also increases, and there should be decrease in the frequency at lower amplitude levels. Okay, the phase will be varying here whenever the signal is changing from negative to positive or positive to negative. See, the phase also will be changing. This is the phase modulation. Okay, now we see how do you generate the FM wave. Means there should be one method which is Armstrong method of FM generation. What is that? Armstrong method of FM generation. Using that, we can able to generate the FM wave. We'll see that. So generation of FM waves, nothing but we can able to generate the FM wave using two categories. One is direct method, another is indirect method. In indirect method, we are able to generate the frequency modulated wave using Armstrong method of generation. See, what is that Armstrong method of generation? See, this is the Armstrong method of FM wave. Armstrong method of FM wave. How do you generate? Using Armstrong method, see what are the signals we are applying here? Here, the first component is crystal oscillator. What is meant by crystal oscillator? It generates the fixed frequency. Okay, this is applied to the combining network and a 90 degrees phase shifter. What happened? Here we are applying to the 90 degrees phase shifter and a combining network. So through this path and this path, then the modulating signal here, the modulating signal is passed through the integrator circuit in order to increase the low modulating frequencies. Is applied to the integrated circuit in order to increase the low frequency signals. So what we are doing, first with the help of crystal oscillator, we can able to generate the carrier frequency. Then through here we can able to apply the modulating signal which are adding in the summer, right? So what is that? The product modulator produces two side bands. Okay, they are in 90 degrees phase shift to each other. Then at the output of combined network, so that is this, we are getting the frequency modulated signal. We are getting the frequency modulated signal. See, first we are applying message signal which is applied to one of the input of the product modulator. Then we are applying one carrier signal. Both will combine in the summer. Then we can able to generate the frequency modulated wave. That is narrowband frequency modulated wave. See the mathematical equations. Just now we said, right, S of t equal to Vc1 into cos of 2 pi fct plus pi 1 of t, where pi of t is 2 pi k1 into 0 to t x of t. Okay, which is nothing but the carrier wave. Then final expression for FM wave is this one. So what is narrowband FM? Narrowband FM means if the value of beta is very less, that is modulation index of FM wave is less than 1, we can say we call as narrowband FM. If the modulation index is greater than 1, we can call that as wideband FM. Okay. Now we see how do you generate FM wave, right? Then how do you get the message signal from the frequency modulated wave? That is nothing but demodulation of FM waves. So here, in order to get the message signal from the frequency modulated wave, we need to follow two steps. What is that? Here the input to the demodulator is FM wave. The FM wave demodulator have to satisfy the following requirements. What is that? The first one is it convert frequency variations into amplitude variations. Okay, first because we are taking the frequency modulated, it is having both high frequencies followed by low frequencies. That's why it should convert the frequency variations into amplitude variations. Okay, then the demodulated circuit should be insensitive to the amplitude changes. It responds only to the frequency changes. Okay. Here it will be also having two types, direct type and indirect type. Okay. Here in this we'll see simple slope detector. What is that? We are applying FM input and which are applying to the simple slope detector. Here there is a transformer which is tuned to the some frequencies. Okay. Then it allows only the frequencies specified by the transformer and does not allow the low frequencies. In this way, whenever we are applying FM input to the tank circuit, it allows only the specified frequencies and rejecting the other frequencies. So first we are taking the FM input that should be converted to the here amplitude modulated input by the help of transformer. Then the amplitude input is applied to the diode and resistor. Then we can get the modulated signal. If you observe here, this thing is similar to the envelope detector circuit. Okay, in the envelope detector also, right, we are applying the modulated signal to the diode and capacitor combination. So first we are applying FM wave, it should be converted to the AM wave, then which is applied to the envelope detector circuit, then we can able to get the message signal back. Okay, this is about your frequency modulation demodulated technique. Now we'll see the receiver's part. So first of all, we'll be having a receiver is super heterodyne AM receiver. So first we'll see what is meant by receiver, what are the steps performed by the receiver. We'll see that. What is that? Super heterodyne receiver. So what is that super heterodyne receiver? The main function of radio receiver is it performs 5 steps. What are those steps? First, it intercepts the incoming modulated signal by the receiving antenna. Nothing but it can able to capture the signal from the receiving antenna. After that, it will select the desired signal and rejecting the unwanted signal from the receiving antenna. It can able to capture all the signal whichever is required, then select that signal and reject the unwanted signal. After that, it should able to amplify its selected RF signal. Then we can able to detect the modulated signal, that is we can able to extract the message signal from the modulated signal, that may be AM or FM. Then once again we need to amplify the modulating signal. Okay, that are the functions performed by radio receiver. So what is meant by radio receiver? A radio receiver is an electronic circuit which picks up the desired signal, which is able to pick up the desired signal and reject the unwanted signal. Picking up the desired signal and rejecting the unwanted signal so that it can amplify the desired signal, then demodulate the modulated signal in order to reproduce the message signal back. So see, this is the block diagram for super heterodyne AM receiver. What is that? I said right, through the antenna we can able to receive the signals. So see, first of all we can able to receive the one message signal and we are able to select the desired signal which is applied to the mixer. What is the mixer does? Mixer is a non-linear device to accept the input and able to produce the sum or difference of the frequencies. To this mixer, one of the input is incoming signal frequency, that is Fs, and other signal is the local oscillator frequency F0. Here what is the condition? We need to maintain intermediate frequency. So for broadcasting of AM signal, we need to possess the intermediate frequency which is 535 hertz. Okay, there should be some intermediate frequency for producing the, for able to transmitting the AM signal. There should be some intermediate frequency. So until that intermediate frequency is obtained, we can able to tune the local oscillator. We should able to tune the local oscillator. Suppose if you are applying some incoming signal frequency and we are applying some low class rate frequency, that difference should be equal to the intermediate frequency of the AM. Then only it can able to receive the signal. Okay. Then which is applied to the IF amplifier. What is that IF amplifier? IF amplifier is nothing but it consists of tuned transformer to allow the selected frequency which is applied to the demodulator. Then demodulator extract the message signal from the amplitude modulated wave because the signal should be weak. So which is applied to the audio amplifier. It can raise the strength of the signal and we can able to get the output from the loudspeaker. See here, the incoming signal is combined with the low class rate frequency through a mixer and it is converted to a signal of lower frequency which is called as intermediate frequency, which is amplified and demodulated in order to produce the original signal. Okay, and we said right, the intermediate frequency amplifier contains a number of transformers. Okay, it provide most of the gain and after the AF amplifier, the signal is applied at the input of demodulator and which will extract the original message signal. Okay, this is that explanation part. So what are its advantages? So no variation in the bandwidth and the bandwidth remain constant. Okay, and it can able to provide high sensitivity and selectivity and high adjacent channel resection. Okay, this is the amplitude modulated super heterodyne AM receiver. Similarly, we'll discuss that FM receiver. So we discuss the FM receiver part. So how do you define FM receiver? We'll see that. So we'll see that receiver FM receiver. See what is the block diagram FM receiver? See, it consists of RF amplifier, mixer, local oscillator, here limiter, automatic gain control, discriminator, de-emphasis, audio amplifier. We said right, basically a radio receiver means it able to capture the incoming signal, select the desired signal, reject the unwanted signal, then amplify the signal, then demodulate the signal, then again amplify the message signal back. See, first the receiving antenna receives the signal of electromagnetic wave and converts into RF voltage. This is applied to the RF amplifier. So the mixer amplifies the mixer able to receive the RF signal and through the low class later it will accept another signal. I said right, the intermediate frequency of FM wave is 10.7 megahertz. So until we can able to get this 10.7 megahertz, we have to tune the local oscillator frequency in such a way that the difference produces 10.7. Okay, then which is applied to the mixer. So we can get the frequency in order to transmit the FM signal. Then after that it is applied to the IF amplifier. So IF amplifier is applied to the limiter circuit. The limiter, it removes the noise in the received signal and gives a constant amplitude signal. Okay, in this way we can able to receive the FM signal back. And what is the use of automatic gain control? Which is used for producing the DC voltage whose amplitude is proportional to the audio signal strength provided by the detector. Okay, this is about your amplitude modulation and its problems, frequency modulation, its generation methods, demodulation methods. Now we are going to discuss what do you mean by entropy and what is meant by channel capacity theorem. See here. So let us assume the source which is able to produce the set of symbols which are capital X equals x0, x1, x2 and so on, xk minus 1, and each possess its probability values which are probability of x equal to xk which equals pk, p suffix k, and this set of probabilities have to satisfy some condition. What is that condition? Summation k equals 0 to capital K minus 1, which should be Pk equal to 1, which is called as discrete information source. Then how do you define information? Because in order to define the expression for entropy, we have to discuss these basic points. Okay, see, let us consider the communication system which can able to transmit the messages M1, M2, M3 having probability values P1, P2, P3. Then the amount of information transmitted through the message possess probability as, what is that? Amount of information Ik equal log base to 1 by Pk, 1 by P suffix k. That is the information. Then how do you define entropy? See here, what is that entropy means? The average information content of symbols, which is called as entropy. See, consider M different messages. There should be M1, M2, and so on, M, which possess probability values P1, P2, and so on, PM. Suppose we are transmitting L messages, a sequence of L messages, and L is very large. Then how do you define entropy? Nothing but, because each message having message value M1, its possess probability P1. We said, right, total sequence of L messages. So for each probability P1 into L, P2 into L, and so on PM. If we are transmitting message M1, which is P1 into L, M2, P2 into L, L message means PM into L. So what is that? The information due to the message M1 is I1 equal to log of 1 by P1, which is base 2. Similarly, the total information due to the all messages, which is nothing but I total equals I1 total. So how do you define I1 total? Just now we have right. I1 total equal to P1 into L log of 1 by P1. So how do you define entropy? By the formula, average information equal to total information by number of messages, which is the ratio of average information by total sequence length. It is denoted by letter entropy H. H equals P1 into log 1 by P1 plus P2 into log 1 by P2 plus and so on PM into log 1 by PM. Okay, this is the entropy. So they will ask the problems like that. See, they'll possess the value of, they'll provide the value of P1, P2. Just we have to find the entropy values by substituting. Let's say P1 is 0.2 means 0.2 log of 1 by 0.2. P2 is 0.3 means 0.3 log of 1 by 0.3. Like that they will be asking. Okay, you have to remember this formula, and you need to remember the base as 2. Base is 2. Okay, then we'll define, what is it? Shannon-Hartley theorem. It is also called as channel capacity theorem. See, the information rate, that is the rate at which how many bits are transmitted per second, we can call that information rate, and channel capacity, which is defined by, denoted by letter C. Okay, Shannon's theorem. What is that Shannon's theorem? State that it is possible to transmit the information with a small probability of error, provided that the information rate is less than or equal to the channel capacity, where information rate is nothing but the product of the small r into h, where h is entropy, the small r is rate at which messages are generated. So how do you define the capital R? That is r in messages per second, h is entropy per second. Okay, so what is the formula for channel capacity theorem? Which is the channel capacity of a signal is C equal to D into log of 1 plus S by N, where B is nothing but the channel bandwidth, S is the signal power. S is the signal power. See how they asking the problem for that. They'll provide the values of see, we'll see the small problem, we get a clear idea. They'll give you the value of bandwidth as well as signal power. Then we have to find out the channel capacity. Simply C equal to B into log of 1 plus S by N. See here, the cathode ray tube is connected to the computer through a voice grade telephone line having a bandwidth of 300 Hz and an output signal to noise ratio of 10 dB. Assume the terminal is having 128 characters. That data sent from terminal consists of independent sequences. What they have given, they they have given the bandwidth of 300 megahertz and they have given the signal to noise ratio of 10 dB and they are said where they are transmitting 128 characters. We need to find the capacity of a channel and also find the maximum rate. Capacity of a channel we have to find and also we need to find the maximum rate. Okay, we need to find the maximum rate. See, so what is the formula? C equal to B into log of 1 plus S by N. What is B? Bandwidth, which is 3000. Log base 2. What is that S by N ratio they have given? 10. So C equal to 3000 into log of base 2. So what is the capacity? They are given 10,378 bits per second if you calculate. Then what they said, they are transmitting 128 characters. And what is the formula for average information content per character? Which is H equal to log of C. H equal to log of C. So H equal to log base 2 into the terminal characters M. So H equal to log M base 2. Here they have given right this formula. See here. H equal to log M base 2. In this see here. So what is the formula for total entropy in characters? H equal to log M base 2. Here they are transmitting 128 messages. So that's why we are calculating that one. See. So H equal to log M base 2. Here number of messages or characters are 128. So we are getting average information content per character is 7 bits per character. And we know right, just now we said what is that average information rate, capital R equal to small r into H. So what is that? How many bits per character we are sending? 7. So 7 RS, which is less than 10,000. Why? Because the capacity of the channel is 10,378. So from this, what is the RS? That is the rate at which information transmitted, which is 14,000. Sorry, 1,482. Okay, it's the about entropy and its channel capacity theorem. Now, just we see what are the properties of entropy. Just we'll be having two properties. Just we see that. What are the properties of entropy? See this. So, what is the property of entropies? The value of entropy is 0 if the event is sure or it is impossible if H equal to 0 or probability associated with the kth message is 0 or 1, which is the one of the property. The entropy value is 0 if the event is sure. And when pk equal to 1 by m for all m symbols, then symbols are equally likely such that the source entropy is given by h equal to log m base 2. Just now we have written right, h equal to log m base 2. And upper boundary of entropy is h max equal log m base 2. See, they have given one example. Calculate entropy value when probability is 0 and when probability is 1. We know, right, the formula for entropy. H equals summation k equals 1 to m pk into log of 1 by pk. If suppose probability value is 1, see k equal to 1 to m, 1 into log 1. So what is that entropy value? 0. That's why we said here the first property, entropy is 0. See, when pk equal to 0, suppose, what is that? Pk equal to 0. That is, with pk tend to 0, the above equation will be 0. So entropy will be 0. Okay, the entropy is 0 for both certain more for both certain and most row messages. And another formula, if there are m number of messages, then entropy of the source is log m base 2. See, if there are m number of messages, so the number of messages should be m. Its probability value is p equal to 1 by m. So the total value is p1 equal to p2 equal to p3 and so on pm. So then h equals k equals 1 to m pk log of 1 by pk. So if we expand this, what do we get? P1 into log of 1 by P1 plus P2 into log of 1 by P2 and so on P3. So finally, we'll get the expression for entropy as this one. Okay, mainly it possesses these three important properties. What are those properties? Entropy will be 0 if the event is sure or it is 0, and when it is 1 by m probability h equal to log m, and when there is upper bound on entropy, h max equal to log m base 2. So in this session, we have covered what is in by modulation, what is in by amplitude modulation, what are the generation and detection methods for amplitude modulation. We have seen some problems related to the amplitude modulation and frequency modulation. Then we have discussed what is in by radio receiver, the types of receivers like super heterodyne AM receiver and super heterodyne FM receiver, and what are the modulation methods for frequency modulated wave and demodulation method for frequency modulated wave. And we have seen what is meant by entropy, what are the properties of entropy, then what is meant by Shannon-Hartley theorem, or we can say channel capacity theorem, and what is the formula for channel capacity theorem. I have seen the problem related to the channel capacity theorem. This is very important problem. Many times in the gate they are asking what is the relation between the channel capacity and bandwidth, the relation between the channel capacity and the bandwidth, which is C equal to B into log of 1 plus S by N. Many times they are asking, so please concentrate. In the next class, we'll see the some more topics. Okay, thank you. I'm closing the session. Thank you. Thank you.